So we're going to start with a few definitions here. We already talked about the secant, which is a line segment that passes through 2 points on a curve. So if my curve looks something like this, parabola, I can pick 2 points, and try to draw a line that actually goes through the 2 points. That's a secant. The slope of that line, as we just finished talking about, is the average rate of change between those 2 points. It might represent something that which might be interesting or it might not be interesting, but that's just the slope formula from grade 9, right? So secant is the line, the slope of that line, slope of the secant is the average rate of change, or we call that AROC. What's a tangent? You may have done these in science class. I don't know if you do them in grade 11. Do you? You do. Okay. What's a tangent? Well, the definition is right there. It's a line segment or line that touches a curve in one and only 1 point. Now, if it's a different kind of a curve, like a cubic, it might pass through the line again, or the curve again. But if it's a short line segment, it won't. So what a tangent would look like, if I pick a point, I'm going to do that better again. It just touches, and I'm drawing these as lines, and the definition says line segments, but it doesn't matter. It touches at a single point. That's a tangent. And you've heard that word, and tangent is a word from trigonometry as well, just like secant, like I talked about before. So why are we talking about tangents when we talk about, when we're doing like quadratics? But there is actually a reason why that's called a tangent, that's related to trigonometry and all of the work that we did, but we're not going to get into that. But you've heard most of you, or some of you at least, have heard the saying before, when you go off on a tangent, like when you're talking about something, and then, like maybe about math, and then you go off on a tangent, and you start telling a story about a squirrel or something like that, right? That's going off on a tangent. And that's directly related to what a tangent line is, because you can imagine that you're following a particular path, and then you go off on a tangent before, I suppose, going back and returning along your path. So if I'm teaching a math lesson and then I start telling a story, I'm going off on a tangent, but I'll eventually resume back onto the original path of teaching the lesson. You know what I mean? So interesting that a tangent line is actually where that statement comes from. So if the slope of the secant is the average rate of change, what's the slope of the tangent line? That's exactly right. It's we call it the instantaneous rate of change at that 1 point, or we call it the IROC sometimes for short. So the little thought experiment that we did on Alec and Gurpreet, and how Gurpreet overall traveled the same distance in the same amount of time as Alec, but at different speeds because they hit traffic. And we said, but over the course of the entire trip, their average rate of change was the same. But a police officer sitting on the side of the road doesn't care about your average rate of change. They care about how fast you're going at that moment. And if at any single moment they catch you going too fast, you get a ticket. You're not like, well, I was just stuck in traffic, so I was sitting there going nowhere for a bunch of time. That's why I'm going fast. They don't care. You know what I mean? So again, sometimes we might care about the average rate of change. Sometimes we might care about the instantaneous rate of change. But if I'm in a car and I'm sitting at a stoplight and it turns green and I hit the gas and I start going, I'm accelerating up to a certain speed, and I would have an average rate of change from the time that I started accelerating to the time I got to my speed that I was driving at. But at any one single point during that time, you could take a snapshot of how fast I was driving. And that's what your gauge tells you is your speedometer, right? The gauge tells you is how fast you're driving at that moment. It's not taking an average. At that exact time. So that's an instantaneous rate of change at a single point. Here's the problem. A tangent line only has one point that's on the curve. How can we find the rate of change of one point? So in science class, you do it one way. That's not how we do it in this room in math class. Don't tell them I said this, but we do it the right way. Okay? Well, that's how they do it in science class. That's not how we're going to do it. But that's right. And that's an estimation. And if you knew the equation of that line, then you could do that. The problem is, and for science, it's fine, obviously, to do it the way that they do it. They would have to teach all of this stuff in order to do it this way. But you're just drawing a tangent line. It's hard to draw a tangent line accurately. So people are going to get different answers. That's an estimation. What if we wanted to calculate it exactly? Here's the problem. Okay? There's my tangent line at that point. That's what we want to know the slope of. Our only tool is the slope formula from grade 9. That's the tool we have for finding slopes of lines. And as Kyle said, if I could find another perfect point on that line, then I could use that. But I can't. So if it's a secant, we're fine. If it's a secant, I got 2 points. I can find the y value of each of those points, which you can see over on the side here, right? Over here, I'm using my slope formula from grade 9. And I'm finding 2 points, subtract the tops, subtract the bottoms, and divide, and I get my average rate of change, because this is a secant because there's 2 points. But the problem is, when I do it with 1 point, look what happens. I'm using the same point twice. I get 2 over 2, 2 minus 2 over 1 minus 1, 0 over 0. Well, what's that? You can't calculate that. That's not going to give us an answer. So 0 over 0 doesn't work. If you thought, oh, well, it's equal to 0. Well, the slope of that line certainly wasn't 0. So that can't be right. Our formula from grade 9 doesn't work when we only have 1 point. Oh dear. Right? Again, if I go back, so there's the line that I'm trying to find the tangent of, that thick red line. As I get closer, as my 2 points get closer, that line is approaching the tangent, isn't it? So I could get closer and closer and closer and closer and closer and closer. And look, it's almost equal to that now. Because I'm really close. I'm at 0.97 as opposed to 1. And watch what happens, okay? So if I'm going to reset. Watch what happens. I'm at 1.5. There's the tangent line. The slopes don't look anything alike. Do you agree? As I approach, my slope was 1.5. Now it's 1.6, 1.7, 1.8, 1.9. You can still see a gap there. Closer, 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 closer. 1.94, 1.95, 1.96, 1.97, 1.98, 1.99. Oh, darn it. What did it look like that value was approaching, though? 2. Yeah. So you could use this estimation technique, or you could just pick 2 points really close together. And if it's a nice number like 2, you might guess and you might be right. And 2 is correct in that situation. But what if it was like 53 over 17? Well, how are you ever going to guess that that's the right answer? By using this estimation technique. So we're just going to kind of copy down some of the values from that demo. when I did it between these two values, I got 1.5. And you could do all this math, but I've done it for us just to save some time. And then as I get closer, it's 1.9. And then as I get even closer, it's 1.99. But if I do it at that single point, using this method, that's from 1 to 1. That's going to be 2 minus 2 over 1 minus 1. 0 over 0. Ah, darn it. Foiled again. I keep trying to do that and it keeps not working. What if we approach from the other side? 2.5. 2.1 as my interval gets closer, but it's from the point I want and a point past it, right? So I'm approaching from the other side. So I'm approaching from here and getting closer this way. So it's the same idea, the slope is now steeper, but getting less steep, getting closer. Whoops, I hit the wrong button. Getting closer and closer to 2 again from the other side, right? So from here, it's 2.01. And if I, especially for, this is a parabola, so the numbers work out really nicely. Whoops, right? For other ones, and it's got a nice whole number slope of 2, so it's easy to see. But you can really see from both sides, like that's pretty convincing. From both directions, it's clearly approaching 2. And I would say, therefore, the instantaneous rate of change, I suppose, is 2 or something like that, if you were going to use this method. We don't like estimation techniques in math class. We want to calculate things. We want firm answers. Right? So if only there was a better way. Turns out there is. So we're going to use this tricky thing, and I'm going to do a little demo here. And maybe come back to it again. There's this thing in mathematics called a limit. And here's what it does. I want the slope of that tangent line. But I know that if I try to use my slope formula, if I try to use it between 2 points, I'm all good. It works fine. When I try to use it on a single point, I don't know if I can do it with this. Yeah, it won't work. We saw in the last example that the line disappears and you can't do it. It's 0 over 0. It'll always be 0 over 0. It won't work. Okay? But we also saw that as these 2 points approach each other, or as one point approaches the other along that curve, the slope gets really close to it. It's just that when I get on that point, it doesn't work. And we saw that in the estimation. So somebody came up with the idea of a limit and said, I know at that point it doesn't work. So what if I just think about the point getting really close, but never equaling it? So it's never going to be 1 point. It's going to be 2 points, but I'm thinking about those 2 points getting infinitely close to each other, infinitesimally close to each other. The way a curve approaches an asymptote. Gets closer and closer and closer and closer forever, but never equals it. That's what a limit is. You don't have to worry too much about what a limit is. We're not doing limits. Limits is the first unit in calculus. So if you're taking calculus, you will learn a lot more about limits and you'll have to know more about them. We're just going to use the notation a little bit. But this is why this is going to work. It's going to blow your mind a little bit. Okay? So that's what we're going to do. Notice that this is my x value. A value is where I want the slope. So as x approaches a and the distance between x and a, and I'm talking about like horizontally along the x-axis, as this distance decreases and as that distance gets closer and closer to 0, my slope is getting closer and closer to the slope I want, isn't it? So that's what limits will accomplish. And we already talked about the difference quotient. We're going to use the difference quotient, but we're going to use it in a tricky way. And we'll talk a little bit later about why this works, because it looks like a trick. So all of that is just a preamble of that demo that we saw, and you've got a picture of the demo to remind you of what it looked like. But let's do an example, and then maybe we'll come back and look at it again. So example 2 says, for the function x squared plus 1, determine the rate of change when x equals 1. Again, our formula that we're going to use won't work at a single point. So I want to do this. The IROC, oh, and by the way, I didn't mention this before. We will use these terms interchangeably, okay? So I might refer to it as the IROC. The question might be talking about the slope of the tangent. I'm not going to write them both down every single time. I usually call it the slope of the tangent, even if it says the instantaneous rate of change or whatever. They mean the same thing. The slope of the tangent is the instantaneous rate of change. The instantaneous rate of change is the slope of the tangent. Slope of the tangent maybe is used more when it's just a line or just a curve, whereas instantaneous rate of change maybe is going to be used more when it's about something. But for our purposes, it means the same thing. So this is limit notation. The limit as x approaches a. All that means is that demo that we just watched. It means x is approaching a but does not equal a. Because if x equals a, everything falls apart. Of f at x minus f at a over x minus a. Is this true? Yes? That's our slope formula? The one that won't work at a single point? But we know what a is. A is this. So f at a equals a squared plus 1 means f at 1 equals 1 squared plus 1, which is 2. So this is the limit as x approaches a. We have to write that every single time because we're not talking about when x equals a. We're talking about it's just approaching it very closely. Of f at x minus f at 1 over x minus 1, which is the limit as x approaches a of f at x, which is x squared plus 1, minus f at 1, which is 2, over x minus 1. Is everybody okay with that? So far, so this is the formula. Top line here is the formula. Okay, it's something you're going to need to know, and you need to start writing the limit notation correctly. But it's just a formula. It's just a slope formula. That's all. But if we want to use it when x equals 1, then I'm still using the slope formula, but I don't have 2 points. So if it was f at 1 minus f at 1 over 1 minus 1, it'd be 0 over 0, right? That's what we can't do. So I'm leaving it as f at x minus f at 1 over x minus 1. So we got to find f at 1. Figure out what that is. Okay, then I can start doing some work here. X approaches a. X squared 1 minus 2 is negative 1. Now what can I do? Come on, what's going on top there? It's a difference of squares, isn't it? And I know some people kind of think like, well, I noticed it was a difference of squares, but I don't know if that's what you're talking about. Well, it's just about observation. So even if, like, you don't know if we're supposed to factor or not, but even if you don't know that, you should still notice that that's a difference of squares. And turns out, yes, that's exactly what we want to do is factor it. And what happened? These divide. This always must and will happen. After it happens, we write the limit one more time. Oh, shoot. I wrote this wrong. This should be, okay, hold on. Sorry, I wasn't thinking about this. Back up at this line. When I subbed in 1 for A, I missed this spot. So go back to that line. This should say 1. It should be as x approaches 1. All the way down, okay? Which I know probably doesn't matter much to you, but that's actually really important. It's important notation. Again, the limit notation is not what we're going to dwell on, but now, if I go back up, the reason why it's important, if I go back up to any one of these steps and I sub 1 in, 1 minus 1 is 0. 1 squared is 1, right? So 1 minus 1 is 0. 1 minus 1 is 0. I get 0 over 0 still. Still doesn't work because the slope formula doesn't work for 1 point. But what happens if I sub it in now? It's going to work. So that's what you do. Okay? So after these divide out, we're going to write this one more time, and then we're going to sub in and solve it. Well, what happened? How does that make any sense? How did we just use the slope formula to calculate it when it doesn't work between a point and itself? Because that's the correct answer. That's right. How does that make any sense? There's strange things happening. It's like you're like, well, no, I'm not going to use the slope formula for a single point. I'm just imagining 2 points, but they're really close together. No, I'm just going to, that's all I'm doing. Hey, math, look over there. Oh, now I am going to do it. Now I am going to use it between a point and itself. And like math didn't notice that we did something tricky here. But there's a reason why this works. We'll talk a little bit about that later. It's not super important. What's important is this is the method for using the slope formula to find the slope of a tangent. And we can calculate it. It's not an estimation, it's a calculation. And but it's strange that when we use a single point and we get 0 over 0 every single time, then all of a sudden we don't. But there is a reason why this works, and it is something that we can make sense of, so we will, but not just yet. So we're going to do a few more examples. You don't have all of these examples in your handout. So you could just do this on your own paper. And what this unit for us is going to be about is learning how to do what we just did with only a few different kinds of functions. So we're going to just be practicing the algebra that's involved. And basically this entire unit is finding slopes of tangents. And we're going to do a couple of other little twists to it, but it's all the same kind of thing using the difference quotient. So our first example was a quadratic. This one is cubic, degree 3, positive leading coefficient, like we know something about that curve. It's not what we're talking about right now, so I'm not going to get into it again. If we were going to do an exam, it'd be really useful to be reviewing all of this stuff again and talking about it. So now we're doing a cubic. And depending on the type of function you start with, you know, the math and the strategies are going to be a little bit different. So like I say, this is kind of what we're working on. Determine the slope of the tangent or the instantaneous rate of change when x equals 1. Everybody got that? So this is how we do it. Slope of the tangent equals the limit. I'm just writing down the formula as x approaches a. People get the notation wrong or just show their steps wrong. So that's something else that I'm going to be talking about and trying to be clear on is how your solutions should look. So you should always start with the formula, which is limit as x approaches a of f at x minus f at a over x minus a. That's just the formula. Then I sub in my value. So for this question, it's when x equals 1. So this equals the limit as x approaches 1 of f at x minus f at 1 over x minus 1. And to continue, I need to know what f at 1 is. So it looks like -3. Sometimes people do the substitution directly in the question. I do want you to show, you don't have to show your work for those, but you have to make the statement. Sometimes people do it like this. And that's fine if you want to do it like that. Or on the side, you can just write f at 1 equals -3. Like you don't even have to show the substitution. So now I'm going to sub in f at x, which is the function x cubed minus 4. X cubed minus 4 minus -3. One major mistake, and again, because we don't really talk about limits, it's a fair mistake, I understand, but I want you to think about it, I want you to hear my words, and I want you to think about this, and I want you to, during your practice, just be mindful and careful. People put the equal sign between the limit statement and this. They say the limit is x, which is 1 equals that. That doesn't make any sense. This is almost like an operation. Like if you're taking the log of something, we're doing the limit of something, of an expression. So it doesn't make any sense to put the equal sign between them. Okay, so the equal sign goes there, then the limit sign, then all of your work. And you just write it every time, and you have to know when to stop writing it. And that's all you need to know about limits for now. So what does this look like? This looks like -4 plus 3. Now what do I do? Who remembers polynomials? Difference of cubes? Is anybody thinking that? That's a difference of cubes. X cubed minus 1 is a difference of cubes. Does anybody remember how to factor a difference of cubes? Sort of. Remember of it. Remember doing it. Remember exactly what the formula was. Maybe not. That's okay. So it's the limit as x approaches 1 of x minus 1. Remember, and then it's x squared plus AB. So x times 1. So just plus x. Oh my goodness, what's going on right now? Plus 1. Where do I have space to write that out? I'll write it out over here. a cubed minus b cubed equals a minus b, a squared plus ab plus b squared, right? Now we kind of remember that? Okay, over x minus 1. We'll look at that. Remember how I said in the last one, this always has to happen? This is just a formatting thing. I want you to write it one more time. X approaches 1 of x squared plus x plus 1. Then you need to show the step where you substitute. And then you can do all of the rest of the work in one step. I don't care how you do it. In this case, it's 3. This is a really big thing because what we've done is we've realized that we can't use the slope formula for a single point, which is what we want in order to find an instantaneous rate of change. But it doesn't work. And so that's why these questions are a lot more work than just the slope formula from grade 9. But that's powerful stuff. And as I've said, turns out this is the seeds of calculus. So this is kind of a big idea. Everybody good? Got a couple more here. The first two were polynomials. One of them was a quadratic and one of them was a cubic, but that part doesn't matter. The strategy, the technique that we used was factoring. So after we did all of the work to kind of get things set up, sorry, I'm going to scroll back up here for a second. We did all this work to get it set up, which is to this step right here. Okay? Then we simplify. And then our strategy is to factor. So whatever you have on top, you are going to be factoring. That's the strategy when you have a polynomial. This is not a polynomial. This is a rational function from unit 3. Or reciprocal function, but a rational function from unit 3. So it's going to require a different strategy. Determine the slope of the tangent to f of x equals 1 over x plus 3 when x equals 4. Okay, so let's get it set up. Slope of the tangent equals the limit as x approaches a of f of x minus f of a over x minus a. Just the formula. Now I'm subbing in, so it's the limit as x approaches 4. In this case, of f at x minus f at 4 over x minus 4. So I need to know what f at 4 is. Am I going too fast or are we okay? I sub 4 into the equation. What do I get? 1 over 7. Right? On the bottom in the denominator, 4 plus 3 is 7, so 1 over 7. Like the first bunch of steps to get this set up are the same steps every single time. Write out the formula, sub in, figure out your y value or your function value if that's how you want to look at it. This is where I sub the function in, 1 over x plus 3 minus 1 over 7 all over x plus 4. So this one looks significantly different from the last one that was a polynomial, or the last two that were polynomials. Are we okay? This is the setup. Now we need to know how to solve this one. What's our strategy? In this course, we're only looking at 3 different types. First one's polynomial. This is the second one. Third one will come in the next lesson. I don't think we're not going to do an example of that one today, or right now. So our strategy for this one, this is the important part that you want to really be following. I look at the top, and I look for a common denominator. The common denominator is going to be 7 times x plus 3. And there's 2 slightly different ways you can do this. And so the solutions may show it a little bit differently. And everybody's different exactly how you want to do it. You can either get a common denominator on top, or you can multiply the whole thing by the common denominator. It's going to get you to the same place in the end. Okay? When I multiply the bottoms, I get 7, x plus 3, x plus 4. Right? What happens when I do it on top? Well, I'm going to do this times that, and this times that. So I'm going to multiply my common denominator by both those things. When I multiply it by 1 over x plus 3, the x plus 3's are going to divide out. Do you see that? So it's 1 over x plus 3 times 7x plus 3 over 1. So the x plus 3's cancel, and I get 7. And when I multiply it by the 1 over 7, the 7's cancel. And I get x plus 3. Is that okay? Like, you need to learn how to set these up for notation purposes, but this is the big part. This is the important part. You need to know how to do that. You need to know what to do, but you also obviously need to be able to do it correctly. Okay, and now I start simplifying, and I'm looking for the stuff to cancel out. So this is 7 minus x minus 3. Oh, it should be x minus 4. Thank you. Yeah, right there. Where did that come from? Thank you. Oh. Okay. All I did was distribute the negative. So this is negative x plus 4. If I sub 4 in here, I'm still going to get 0 over 0. Negative 4 plus 4 is 0. And when I sub it in on the bottom in that bracket over there, I get 4 minus 4, which is 0, which cancels out all the rest of the junk. So I still get 0 over 0, because the slope formula for 1 point doesn't work. So what do we do now? Yeah, we can. We're still going to have it, but we're going to factor it out. And this is what you have to be, like, this has to be at the forefront of your mind when you're doing these, is I need the top to have an x minus 4 in it, because that's the part that has to cancel out. Because once that happens, we can do what we need to do. Limit as x approaches 4 of negative 1 over 7 x plus 3. You are only allowed to drop the limit part on the side when you sub in. Four plus 3 is 7. 7 times 7 is 49, so it's negative 1 over 49. Any questions on that one? We're going to do one more. Two more. Do we have time for 2 more? Shoot. Any questions on that one? Okay, I'm going to skip 5 and go to 6. So that's why, just because we're going to run out of time here. I thought I had lots of time. I forgot there was an extra example in there. So example 5 is another rational function. The difference is it has x on top and bottom, but the strategy is the same way. So it'll be online in the lesson. You can take a look at it there if you want to see another example of how to do it, but it's the same as the one we just did. Same idea. Common denominator. This one's a bit of a different kind of question, so we have to see this one. So for the function f at x equals x squared plus 1, that's the same function we've been kind of looking at earlier on in this lesson. But this question says determine a simplified expression for the slope of the tangent at a. So this one's a little bit different. So I'm going to get started. All I'm going to do is write out the formula. I know you're trying to copy down the question. You can copy it down after too if you want, of course. Slope of the tangent equals a limit as x approaches a of f at x minus f at a over x minus a. The difference is I don't have an a value. So f at a isn't a number, it's not 5. It's a squared plus 1. So when I sub in, I get that. Is everybody with me okay? So when when the instructions are determine a simplified expression for the difference quotient or for the slope of the tangent, you have to leave it as a. Okay, I'm going to continue. X squared plus 1 minus a squared minus 1. So all I'm doing is simplifying. I distributed the negative. The ones are gone. Now what do I do? Not common. Difference of squares, right? But factor is the important part. So again, this was a polynomial. So you are always going to factor at this point. Watch. Watch. So I've canceled it out. I write it one more time, and then I can sub in. There's my simplified expression, 2a. So for B said determine the rate of change when A equals 2 or when X equals 2. Questions are going to say it a little bit differently. Don't worry about whether it says A or X. It's not really important. Okay, so at A equals 2 means the slope of the tangent is 2 times 2, which is 4. We're done. So kind of like an average rates of change when we came up with a simplified expression for the difference quotient. If you were going to do a bunch of these for the same function, if I was going to do a whole bunch of slopes of tangents at different places along a function, it would be a lot easier to come up with that simplified expression and then just sub in your A values or your X values. Not really the point for us. You're not going to have to decide when it's better, when it's more efficient to do one or the other. You're just going to follow the instructions. If the question just says, find it at this point, or if the question says, determine a simplified expression for, then you're going to do one or the other. Okay? But you do have to need to know how to do both.